Welcome back to Real Analysis. Today we are going to talk about lower bound, upper bound, supremum, and infimum. What is a lower bound? A lower bound is a number and it is associated with a particular set. So let's have this definition. Let S be a set of real numbers. A number L is a lower bound of S if and only if S, which is an element of the set S, is greater than or equal to L, and this must be true for all elements S. Now, if you can find a lower bound for the set S, we say that the set S is bounded below. Here's the definition. The set S is bounded below if and only if S has a lower bound. As you can see here in the illustration, we have the real number line and we can identify elements S, S sub 1, another element, say S sub 2, and any arbitrary element of the set S must always be greater than or equal to a lower bound. For this case, I have placed the lower bound here and that is represented by L. Take note, however, that the lower bound may not necessarily be unique, so you may identify several points here in the blue ray, and each of these points in the blue ray would be less than or equal to all elements of S. There are also cases that the lower bound is included in the set S, but it's also possible that the lower bound is not part or is not an element of the set S. All elements of the set S must be greater than or equal to the lower bound. In other words, the lower bound must be less than or equal to all elements of the set S. S is described as bounded below and L is referred to as the lower bound. You can identify several points in the blue ray in the same manner that you can identify infinitely many lower bounds for the set S. Among these lower bounds, we can identify the greatest of them all. Thus, we need to talk about the infimum. What is the infimum? It's the greatest lower bound. Here is the definition. The number m sub 0 is a greatest lower bound of S if, number 1, m sub 0 is a lower bound of S, and number 2, m sub 0 is greater or equal to every lower bound of S. So this is the greatest lower bound, and it is referred to as infimum. In symbols, we write INF, inf, and we write the symbol for the set. There are cases when the infimum is not an element of S, but whenever infimum is an element of S, then we say that this infimum is in fact the least element of the set S. So as you can see here in the illustration, I have used the yellow ray to represent the set S. So you can just imagine that the end point of this yellow ray will serve as the greatest lower bound if indeed this greatest lower bound or infimum is the least element of the set S. Once again, let me emphasize that if the set S has the least element represented by S sub min, then the infimum of the set S is equal to S sub min, which is the least element. For example, we have 3 as the least element, so 3 is the infimum. That means the elements of S such as 4, 3.5, say another element 5 must be greater than or equal to 3. So take note, all elements of S must be greater than or equal to the infimum. Of course, we have here the lower bounds, 2, 1, 0, -1 as the lower bounds. 3 is in fact also a lower bound. So among these lower bounds, 3 is the greatest of them all. For this example, 3 is the greatest lower bound. It's the least element of the set S, and it is the infimum. Of course, we also have the upper bound. Here is the definition. Let S be a set of real numbers. A number M is an upper bound of the set S if and only if the element S is less than or equal to this upper bound M, and this must be true for all elements of the set S. In the illustration, the upper bound may be any point on the blue ray, and we can identify several upper bounds for this example. We describe S to be the set that is bounded above, and M is considered to be the upper bound. If we have infimum as the greatest lower bound, we also have supremum as the least upper bound. Here's the definition. The number m sub 0 is a least upper bound of the set S if number 1, m sub 0 is an upper bound of S, and number 2, m sub 0 is less than or equal to every upper bound of S. In symbols, we write SUP followed by the symbol for the set. For this example, we have sup S. Yeah, that's the supremum of S. As shown in the illustration, we can identify several upper bounds for the set S, and these are the points on the ray that is color blue. So one of these points may be the m sub 0, and that is the supremum. Suppose the set S is the set containing X such that X is less than 5. So this is the set S, so 5 is not part of the set S, but obviously it's the supremum. But we can also identify several points here, several numbers such as 6, 7, 8, 9 to be the upper bounds. But 5 is the least of these upper bounds. For this case, S doesn't have the greatest element. Yeah, we cannot identify the greatest element. Can you? But if the set S has a greatest element, we call that as S sub max, then the supremum of S is equal to the greatest element. There are cases that a set has both upper bounds and lower bound. If this is the case, we call this particular set as a bounded set. There are some propositions that I want you to be familiar with. The proofs of these propositions may be explained soon. So the first one is about uniqueness. So a set S can have at most one least upper bound. So it means that a set S may not have the least upper bound. That's the meaning of at most. Or if it has the least upper bound, then there should be only one. Similarly, a set S can have at most one greatest lower bound. So I just would like to emphasize at most. It may not necessarily have an infimum, but if it has an infimum, then it should be only one. Another proposition is the least upper bound theorem. It states that if a set S is bounded above, then it has a least upper bound. It means that the existence of the supremum is ensured as long as the set is bounded above. In a similar way, if a set is bounded below, then it has a greatest lower bound. The fourth one is, let S be non-empty and bounded above, and M be the supremum of S. Then for every epsilon, which is greater than 0, there exists an element S of S such that M minus epsilon is less than S and S is less than or equal to M. So let's have this as an example. Say we have the set S, it's bounded above, and its supremum is M. So we'll have M here, and then we can identify any positive number, and we call that as the epsilon, and we subtract that epsilon from M. So we can identify here a point on the line, and this point is going to be represented by M minus epsilon. So we just simply subtracted epsilon from M. So epsilon is that length. So we can identify an element S here in between M minus epsilon and M. It's also possible that the element S is equal to M, which is the supremum. There are cases that the supremum is infinite, so we have number 5. If sup S is equal to infinite or infinity, then for every n greater than 0, so this is any positive number, there exists an element S of S such that this element is greater than n. We can consider the set of real numbers to be the set having a supremum, which is infinity. Then we can draw a real number line, and this is going to be the representation of the set. So this is the real number line. Its supremum is infinite. And then if we identify a number n for every positive n, then we can identify an element of this set which is greater than that particular positive value n. And we can always identify an element of the set which is greater than any positive number. Are there sets with no lower bound or upper bound? The answer is yes. A non-empty set S has no upper bound if and only if the supremum of S is equal to infinity. I showed you a while ago that the set of real numbers has a supremum of infinity. But take note that this set S must be non-empty, and that is when the supremum of S is equal to infinity. In a similar way, a non-empty set S has no lower bound if and only if the infimum of S is equal to negative. This time around, it's negative infinity. But we have to be reminded that infinity is not a number, and so we cannot perform addition or subtraction. This is just assigning infinity as the infimum or the supremum whenever this set that is given has no bounds, lower bounds or upper bounds. You may refer to these sources for further readings, and remember that it is important for us to keep the foundation strong and start building a sustainable future in real analysis. This is Ma'am Rose saying goodbye, and I do hope that you're going to click like and subscribe. See you in the next video.